Well, hi, this is Bob, and we're getting ready to take a look at section 3.3, which is graphing linear equations in two variables. And I'd just like to remind everybody of what we've done so far in chapter 3. We have learned how to plug in some x and y pairs. Well, actually, the first thing we learned was how to graph x and y pairs on the coordinate axis system, or the Cartesian plane as it's also known. And then we were able to plug in, if they gave us an x and y pair, we were able to plug in the x and y pair and see if it satisfied the equation that they gave us. And we might recall that the equations are in the form ax plus by equals c. Then we also learned how to, along the same lines, we learned how to plug in x or y, and let's say, for example, we were given an x term, we were able to plug that in and find the corresponding y term. And of course, we could plug in the y term and find the corresponding x term. And we also plugged in x-y pairs and found out if they satisfied the equation. And then if they did, where we left off on this, we said that that point was on the line that the equation determines. Anyway, I think what we'll do is we'll start off by following the book's idea on page 175. They tell us that x and y equals 5, and what they want us to do is to draw a picture of this graph and then see what the graph really means in terms of x and y pairs. So we're actually relating this more to drawing the graph now than just seeing, if points work with the equation that they gave us, or whether a point is on the line or not. So what we can do is just think of some numbers for x and y that add up to 5. For example, if x is 0, y would equal 5. If x is 1, y would equal 4. If x, remember the first one's always x and the second one in the ordered pair is always y. If x were 2, then y would be 3. And if x were 3, y would be 2. And if x were 4, y would be 1. And if x were 5, y would be 0. And of course, we could use, like, say, well, x is -1, and then y would be 6. And if x was -2, then y would be 7. And if x was a half, then y would be 4 1/2. Or if x was 1/10, then y would be equal to 4 9/10. By the way, we don't normally use fractions and decimals to plug in for x and y, but I'm trying to show here that we have an infinite number of ordered pairs that would satisfy the equation x plus y equals 5. Turns out we only need to graph 3 of them to get the line. Actually, we only need to graph 2, but we'll see later they ask us to graph 3 points. Find 3 points and graph them, put them on the coordinate axis system, and then hook up the 3 points because they will determine a line. 2 points actually determine a line, but we do a third point for kind of insurance. Anyway, let's just take a look at a few of these points here. Let's say that this represents 0, 5, and when x equals 1, we saw that y equals 4, and when x equals 2, y equals 3, and when x equaled 3, y equals 2. Now, I'm not using a graphing grid here, but I'm sure you can see that this is pretty close. Let's say when x is equal to 5, y would equal to 0. Y would equal 0. And you can see that these points fall on a nice line. In fact, you could even see where I said if x equals -1, y would be equal to 6. Okay, now so a whole number of things come to play here. One is once I've hooked up the points, and we only need 3 points, but we put little arrowheads on the line to indicate that the line stretches infinitely in both directions. And that also tells us that there are an infinite number of solutions to x plus y equals 5, and the line that we just drew represents those solutions. And by that I mean anywhere I touch this line, the xy point will add up to 5. Okay, and remember the line stretches out forever in the second quadrant and stretches out in the first quadrant and throughout the fourth quadrant. Okay, so that's the graphical significance of that line. Okay, well, they give us some information on the top of 176. It's a little bit of theory, but we'll try to do some good examples to support the theory there, or to make the theory a little more understandable if necessary. And the first thing that they tell us is when we have an equation in the form of ax plus by is equal to c, that's something like maybe 2x plus 5y equals 10. They tell us that a, b, and c are real numbers, okay, and we know what the real numbers are. And in this case, a would equal 2, b would equal 5, and c stands for constant, and that in this case would equal 10. As a reminder, the 2 in front of the x and the 5 in front of the y are called coefficients. So we could identify these coefficients as I just did with a equal to 2, b equal to 5, and c, the constant term, is 10. And then the next thing that they want us to know is that this will determine a line, or as we call, a linear equation. Okay, and it's going to be in 2 variables, of course, because we've been graphing these on x-y axes when we have x's and y's. So we've got a linear equation in 2 variables, and that can be shown in a coordinate axes or Cartesian plane. And there's one more thing that we need to know, and that when an equation is in the form of ax plus by equals c, when the x and the y terms are on the left side of the equation and the constants on the right side, this is called standard form. Now, for those of you that had a little algebra before, you may know there's another form. It's called the point-intercept form of an equation. And we'll be looking at that a little later in Chapter 3. But right now, they've introduced us to the standard form, and we are going to do some graphs using the standard form. Now, one thing that's really important that when we're doing these types of graphs, and they've given us a lot of ideas on this in the present, or in the past, and now we're going to see all these ideas fleshed out. What we like to do is graph in y equals, get y by itself, and then have the other members of the equation on the right side, because remember what we normally do. We choose, in the best of situations, we choose a few values for x, and we plug them in and see the corresponding values of y, and then we derive some xy ordered pairs, which we plot. Okay, so the idea is, like in example 2, which is 3x minus 1, once we get, that's just a rearrangement from the standard form into the a y by itself form. And then we can choose values of x, plug them in, and find the corresponding y value. But I'm getting just a little bit ahead of myself. Here's what they tell us before this in order to draw a graph. This is in the strategy part on 176. Find any 3 ordered pairs that satisfy the equation. 2 is enough. 2 points determine a line, but 3 is good for an insurance in case we made a calculator error or a mental error, which, as I've shown you, is very easy to do. So we check ourselves, and then we graph the 3 ordered pairs on a coordinate axis system. And then we draw a line through the three ordered points and stick arrowheads at the endpoints of the line. Okay, now I think we're ready to do 3x minus 1, and I'm going to use their numbers just so we can follow along with the book's example here. The book plugged in 0, 2, and minus 1. Now, those may not have been the values I would have plugged in, but they're certainly good values. I would just normally plug in like 0, 1, and 2, but it's fine to plug in 0, 2, and minus 1. The idea is they're going to be close. The graph is infinite, and we don't want to get a big blackboard to show part of the graph. We only want to take a look at the graph around the origin and a few spaces in all four directions. So what I'll do is here's where we're going to be graphing. I'll just throw out a few hash marks here. And let's go find our points. Okay, this is of course our x-axis and our y-axis. When x equals 0, y would equal 3 times 0 minus 1. So 3 times 0 is 0, y equals minus 1. Remember, that implies the point 0 minus 1. When x is equal to 2, I'll bring these other calculations down here. When x equals 2, we get 3 times 2 minus 1. And 3 times 2 is 6, minus 1 is 5. So that defines the ordered pair 2, 5. And when x equals minus 1, we get y equals 3 times minus 1 minus 1. That would be minus 3, minus 1, or minus 4. So now we go and hook up we plot those points and hook them up, and that will be the graph of y equals 3x minus 1. 0 minus 1 is right here on my graph, and 2, 5 would be right here, and minus 1 minus 4 would be right here. Now, those points, even though I'm not using a graphing software here, those points lie nicely on a line. And remember, I put the arrowheads on and I write y is equal to 3x minus 1, and so we're done. But I want to make one more point here. This line is composed, or understood to be composed, of millions and millions and millions of individual points, and each one of those points have an xy coordinate. And when we plug in the x, in other words, when we plug in the x and y, as we did in the previous lesson, all those points will satisfy the equation y equals 3x minus 1. Okay, and of course a point that isn't on the line, if, for example, whatever this point here is, if we plugged it in for x and y, it would not satisfy the equation y equals 3x minus 1. All points on the line do satisfy. Any point not on the line won't satisfy. Okay, well, I want to do another one here just because this is so important. This is not a long lesson, but it's such a crucial lesson for going on to the subsequent lessons. And of course, the other thing I wanted to mention is that they're going to give us 2 other methods to draw these graphs. This is just the first method that they give us. Okay, now on example 3, halfway down page 177, they give us the equation y is equal to minus 1/3 x plus 2. Okay, and we're supposed to draw the equation, we're supposed to draw the graph that this equation represents, and we've got one little bit of something different here, and that's that we have a fraction for the number in front of x. In other words, there's a 3 down below there. And I'd like to remind you that when we're drawing our graphs, or even when you're using your graph paper, you can find numbers like 1, 1 or 1, 2 or 0, 0, but it's almost impossible to accurately find fractions on this graph. So this problem brings up something called domain, and domain is another way of saying, well, what value of x are we going to choose to plug in and solve for y? And I think you can see that if we can certainly plug in 0. That's always the simplest one and always works for us with this type of equation. But just say, for example, we plugged in a 2 for x. That would give us 1 minus a third times 2, which is minus 2/3. And when we added 2 to that, we'd get positive 1 1/3. Okay, it would be very hard for us to find the point 2 and 1 1/3. Okay, we can find the point 2, 1 or 2, 5 or 3, 7 or whatever, but we would have to guesstimate to find the point 2 and 1 1/3, even though that point is going to indeed be on our line. Okay, so what we try to do when we're drawing the graph is we try to choose values of x, or the domain, that makes our y value come out to be a whole number, or integer, maybe better said. And so that's why they chose -3 and 3. Actually, again, 2 points would do, but we're choosing 3 values for x. That's why they chose those numbers for x. And you can see this happening when I evaluate here. We have the work in front of us there, so I'll just go ahead and set them up. Very simple when x is equal to 0, because minus a third of 0 is 0, and we end up with x equals 2. So that would be our first point. And I'll go ahead, when x is 0, y equals 2, and I'll go ahead and graph that point. Now, watch what happens when x equals 3. We get y equals minus a third of 3 plus 2. Well, the 3 on top and the 3 on the bottom cancel out, and we get y equals minus 1 plus 2, or just y equals 1. So for x equals 3, y equals 1. Now, the last point we're going to use, we're going to plug in minus 3. Y is equal to minus 1/3 of minus 3 plus 2. So minus a third times minus 3 turns out to be plus 1, and 1 and 2 are 3. Okay, so this of course implies 0, 2, 3, 1, and minus 3, 3. And we are going to go find those values and plug them in. I'm sorry, we've already derived those values, and we're going to go graph them, and ideally, unless I made a mistake, they're going to be on the same line, and then we're going to hook that line together. Now, if one of those points does not lie on the same line, then I made a mathematical error. So remember, 2 points is just enough, but 3 points is an insurance, kind of an insurance policy in case we made an error. So I've already shown 0, 2. Here is x equals 3, y equals 1. And the other one was minus 3 and 3. Minus 1, minus 2, minus 3. Well, even on my rather crudely drawn coordinate axis system, when I draw a line through these, they look pretty close. In fact, I know those are on the line because I can look on the book there, and I had the answers, and you can look up on the top of 178 and see it much more nicely drawn there in terms of the actual graph on a coordinate axis system, or on graph paper. Anyway, so again, I've got the arrowheads on there like they do, and I remind us one more time that any place on this line, and this line is composed of infinite number of points that are also on the line, and if we were to take one of these points and plug in the x value and the y value into the equation. In other words, if we took the coordinate, the y value, plugged in the y value and took minus a third of the x value and added 2, the point would satisfy the equation y equals minus a third x plus 2. Okay, and of course, if we plugged in 0, 0, why don't we just do that as a final review here? Here's the origin, which has a coordinate 0, 0, which is clearly not on that graph. Watch what happens when I plug in 0, 0 into our equation up here. It would give us 0 for y equals minus 1/3 of 0 plus 2. Okay, so that would be like saying 0 equals 2, which of course is false. Therefore, that point is not on the graph, and we can see clearly, since we now have derived the graph, that it is not on the graph. Okay, well, here's the most important thing we've done in this section so far. And remember I said we normally like to get y by itself if it's not by itself already, and then choose some x values to plug in. And we learned how to do this in Chapter 2. So here's example 4. We have the equation, and again, this is still on page 178, 3x minus 2y equals 6. And that's a positive 6 over there. And what they want us to do is, because it would be hard it's harder to get some xy pairs for this equation. And what we normally do is, if y isn't given to us by itself, we get y by itself. Okay, so to get y by itself, we would add a minus 3x to both sides. We know, of course, the minus 3x and the 6 do not combine, because minus 3x is a variable term and 6 is a number. Then the last thing we do is divide everything by minus 2. So we're really dealing with y is equal to positive 3/2 x minus 3. Okay, now I'm going to use the points that the book does here, and the first thing I'd like you to notice, of course, is that the book chooses for x, it chooses 0. That's always a simple one for us, but it chooses numbers that the 2 goes into evenly. Notice at the bottom of this equation, the coefficient of x there, when we get y by itself, is 2. And so we're going to choose numbers that 2 go into for x, so we don't end up looking for fractions, which are pretty impossible to get exactly, unless we have much finer graph paper, to plot on a graph. So the book chose 0 and 2 and 4 for x. Now, you could have chosen minus 2 or minus 4, or, you could even choose 20, but then, of course, your graph has to be much bigger. Anyway, we'll get the points first by following their plug-in logic, and then I will go ahead and mimic their graph on the top of 179 there. And I think we can talk our way through these. 3/2 of 0 is 0, so y equals negative 3. Okay. 3/2 of 2, the 2's cancel, and 3 minus 3 is 0. So when x equals 2, y equals 0. And when x equals 4, 4 over 2 cancels and leaves us a 2 on top. 3 times 2 is 6, and 6 take away 3 is 3. So we're going to plot 0 minus 3, 2, 0, and 4, 3. And ideally, they will fall on the same line. Actually, I think what I'll do is I'll ask you to, no, I'll just go ahead and plot them here. That will be one valuable thing to do in terms of our graphing here. Okay, so we had 0 minus 3. Okay, and then we had 2, 0. Now, of course, those are going to define a line because 2 points define a line, but we've got our insurance point coming up, and our insurance point, we plugged in 4 and got y equals 3. One, two, three, 4, 1, 2, 3. Okay, so it appears to me that those points are correctly graphed. So, and they certainly appear to be on the same line, although, you know, when you do this on graph paper, you use a fine pencil, sharp point, and a ruler. But these are certainly on the same line, and we can approximate that graph pretty closely. Now we draw our line through, and I'll put the name of the graph again. The name of our graph is 3/2 x minus 3, y equals 3/2 x minus 3. Okay. So this brings us to the last example here on page 179. And this again, remember I said that there's about 6 or 7 individual pieces of the puzzle to get all of them working for graphing. We need all the individual ideas working together. And so we'll look at these last 3 graphs here. And this is example 5. Y equals 1/2 x, and then we just have the graph of x equals 3. However, for x equals 3, I caution you, this is not on a number line, this is in a coordinate axis system, and so it's going to look different. And then for c, c is plug in y is equal to -2. Okay, so let's look at y equals 1/2 x first. Okay, well, when x is equal to 0, 1/2 of 0 is 0. When x equals 2, then y would equal 1/2 of 2 or 1. When x equals 4, y equals 1/2 of 2 or 2. Okay, now here's the important thing on this one. Notice before, like on our last 2 equations, our previous one was y equals 3/2 x minus 3, and the one before that was y equals 1/3 x plus, minus 1/3 x plus 2. We had some number being added, subtracted to the x term on our last 2 examples. But when it's just y equals something times x, and there's no constant term afterwards, that's a good thing to tell us that the graph is going to pass through the origin, or 0, 0. You'll discover this by plugging in as soon as you plug in a 0, you'll immediately see the other term is 0. So here is x equals 2, y equals 1, and here is x equals 4, y equals 2. Okay, but the important thing on this is when you have an equation in the form of, I'll tell you a little bit on the next page what they're going to say here. When we have an equation in the form of y equals m times x, and for right now, it doesn't matter what m is as long as it's not 0. That means that the line is going to go through the origin. Okay? Now, it's nice to know about that ahead of time, but even if you didn't know, the first thing you would do is plug in 0 for x, and let's say, for example, you had y equals 3x, and you plugged in 0 for x. You'd get y equals 3 times 0, or 0, so you immediately would get 0, 0. But this is a nice little thing to know ahead of time. Now, another really or equally important idea here is what happens if we're just, now remember, here's our general form of the equation. ax plus b y equals c. Let's say that we end up graphing, and remember we're in a coordinate axis system here, and they say, well, draw a graph x equals 3. Well, they don't mean draw x equals 3 like on a number line. They mean x equals 3 on a coordinate axis system. And it turns out that it's a vertical line. Remember, anywhere that I touch on this line here is going to have 3 as the first coordinate. For example, here would be 3, 0. Maybe here would be where x equals 3 and y equals 4. Maybe down here is where x equals 3 and y equals negative 3 or something. But it's very important to notice that each of the terms for x on that line are x equals 3. And you could see how we could adjust this equation here. So in other words, when we have this equation, if we had something like x plus 0 times y equals 3, in other words, if there were no y term, which sometimes happen, then we would just end up with x equals 3. And we could certainly graph x equals 3 on the coordinate axis system. But it looks different than it does on a number line. And remember, anytime that you see a vertical line, and that's another way of saying that it's parallel with the y-axis, that means that it's a graph of x equals a constant. And we normally write that as x equals a. When x is equal to a constant, by convention, we write x equals a. And in this case here, the a would be 3 for the one that we just did. So that's why we said just x equals 3. Don't let the use of letters, like a second ago we saw m in front of the y equals a half x from the top of the next page. I'm trying to put both lessons together, or both ideas together, and I will come back and finish on the top of the next page there. But I'd like to show why I'm going along also. Okay, let's look at that last example then. And this is the one where they say, draw y equals minus 2. Okay, well, let's look at a graph. It turns out all graphs of x, just x, are vertical and parallel to the y-axis. Here's where y equals minus 2 on the coordinate axis. And it turns out that a line going through minus 2, and it's flat, obviously, not vertical. It runs from left to right, and it's parallel to the x-axis. Any graph that's flat, running from left to right, and parallel to the x-axis will be a graph of y equals some constant. In other words, constant is just a fancy name for a number. Okay, and we have a special way of saying that also. We summarize that by just saying y equals b. Okay, so we saw when we have a graph of x or a vertical line, then we generically name that x equals a, and when we have a graph of y equals a constant, then we just generically call that y equals b. And in this case, we can see the constant that b equals would be negative 2, so we say, well, y equals negative 2. Now, let's show why, another way of showing y equals negative 2. Here would be the point roughly negative 2 for y and negative 2 for x. Okay, let's say that right here would be, here's another point. The name of this point would be perhaps x is equal to 5 and y equals negative 2. Okay, here of course would be x is equal to 0 and y equals negative 2. Okay, anywhere that we touch on this line, the y-coordinate is going to be negative 2. The x-coordinate will change. Here we saw the x-coordinate's negative 2. Here we saw the x-coordinate of the ordered pair is 0. And here we saw the x-coordinate of the ordered pair is 5. Okay, well, this is summarized on the top of page 180. And they show us 3 graphs. And the first one is when the graph goes through the origin, it's called y equals mx. And then the second one is when when x is a vertical line, and there's basically I've shown that there's no y term available there, or y is equal to 0, then we say that x equals a. Now, if I knew this point right here where x passes through, then I could maybe it's 3, for example, and I say, okay, x equals 3. But when we just have the raw graph of a vertical line, we say that's x equals to a. Although we could have used z or w or something else for it. Okay, then finally the last one is when we have the graph of y. This would be like in our a plus b plus c equation, where the number in front of x is equal to 0, coefficient of 0. Then we just have the y term there, and we wherever y crosses that wherever the graph crosses the y-axis, that's the point we consider 0b. Just like where the point crosses the x-axis, we consider this one a 0. Okay, that we just don't know what a is in that case, and here we know that x is 0, but we don't know the y term. Maybe somebody later comes along and says, well, you know, that's really 0 for x and 3 for y. Then we would say, well, b equals 3. Okay, well, that's going to be very important for the next lesson when we start talking about slope and y-intercept. And it turns out that where the graph crosses the x-axis is called the x-intercept, and where the graph cuts across the y-axis is called the y-intercept. And that's very helpful when we're going to do some graphing using another method. Okay, well, I have a few homework questions picked out. And I again can't stress enough the importance of this lesson for how it's not only important in its own right, but what it's going to do for us in the next section. But let's do number 2 first. This is in the homework. It's x minus y equals 3. Oops. Now, instead of us getting y by itself, which would be the normal thing to do, oh, by the way, after we do that, they want us to graph the equation. Instead of doing it the normal way, getting y by itself and plugging in for x, they're asking us to, for one more time, to choose some ordered pairs that work. Okay? Now, how about if, let's say, for example, let's use some ones where we get some easy numbers. Let's say, for example, that x was equal to 4. Well, if x were equal to 4, then 4 take away 1 would be, oh, I'm sorry, they have actually told us the numbers they want us to use. Okay, so I got a little bit ahead of myself here. On number 2, they want us to plug in for x 0 and find out what y is. And then they want us to plug in 2 for x and find out what y is. Then they want us to plug in negative then they want us to plug in 0 for x and 0 for y and see what x is. I have to tell you, this doesn't have a lot of practical purpose, but it is good practice for plugging in one value into an equation and finding the other value. So let's start off with plugging in x is 0 first. Okay, that would drop out and we get the opposite of y equals 3, or y equals minus 3. And then if we plugged in 2 for x, we'd get 2 minus y equals 3. We'd subtract 2 from both sides, and that would give us minus, or the opposite of y equals 1, and then the opposite of y equals 1, we would divide both sides by minus 1, and we would get y equals negative 1. Okay, the last one we're going to plug in y is 0, so it would be x take away 0 equals 3, and of course that's just x is equal to 3. Well, now that we have these 3 points, we're going to plot them on a graph. Okay, we have 0, negative 3, which would be down here. And then we have 2 minus 1. And then we have 3, 0. Now, if the points that I started and then realized that I had forgot to use the points that they wanted us to use, had we have chosen 6 for x, for example, and 3 for y, that point would also be on the graph. Okay, but we used their points in this particular question here. Okay, and then the other one I wanted to look at is 8, just because they want us to do it in this method. Eight says y equals 3x. Now, they want us to plug in negative 2 and then 0 and 2. Okay, now the first thing, maybe you remember this. In fact, I'm going to plug in 0 first, but this number does not have a plus or a minus, some constant after it. So the graph of y equals 3x is going to go through the origin. That's just a little reminder there. I'm going to plug in 0 first, and we get y equals 3 times 0, which is 0. So we have now established that 0, 0 is a point on the graph, which means the graph runs through the origin. Let's plug in minus 2. Y equals 3 times minus 2. That would give us minus 6. And when we plug in plus 2, we get y equals 3 times 2, which of course equals positive 6. By the way, if I want, I can go up by 2's on my graph. And okay, so in other words, this would be 2 and 4, and this would be minus 2 and minus 4, etc. So minus 2 and minus 6 would be down here at the bottom. And then 0, 0 would be right here, of course. And then 2, 6 would be up here. Oops, I got a little too high there. Okay, now notice I've changed. Instead of calling 1, 2, 3, 4, 5, 6, I've gone up, or I've used 2, or gone up by 2's in each case here. So this would be, this point here would be 2, 6. And then of course I would hook these together, keeping in mind that the graph extends in both directions, and that there are many other points that are on that line there. In fact, there's an infinite number of points. Well, let's take a look at question number 13. Thirteen is y equals a half x plus 3. Now, this is going to be an easier question for us because the y is by itself, like it was in the previous question, and they've given the numbers they want us to plug in, -2, 0, and 2. Remember, in question 2, we had to come up with our, they gave us the numbers, but we had to do some extra work. Here, it's just a matter of taking a half times the number we're going to plug in and then adding 3 to the result. I'll start off with 0 first because that's always the easiest one. When x equals 0, y equals 3. Then I'll plug in -2. Okay, well, a half times -2 gives us -1, and -1 and 3 is 2. Notice again that they chose, when they chose -2, that allows us to come up with a whole number or an integer for an answer. And we can find the ordered pair -2 and 2. As I said before, we want to avoid fractions. And then the last one is we're going to plug in 2 for x. And that cancels and leaves 1, so y equals 4. So we're supposed to graph this one also, just get an idea of it. Okay, -2 and 2 and 0, 3 and 2 and 4. I need to go up one more there, but 2 and 4 would be about right here. Now again, when you are doing these on graph paper, it's going to look much cleaner, and your line won't have a little wiggle in it or anything like that. It will indeed be straight. But this is more than enough here for us to get the idea of what's happening and what the graph looks like. So this, what I've just drawn, is indeed the graphical representation of y equals a half x plus 3. Okay, well, we've got just a couple more to go here. Here is question number 18, and it's 3x plus y equals 2. However, this time they want us to, before we had y given to us, so we were just able to directly start plugging in, this time they want us to get y by itself. And of course, it won't be too difficult in this case because there's a 1 in front of the y already, so and this is a plus 2 over here, so we add a -3x to both sides. And we end up with y equals -3x plus 2. And since there's a 1 under that x, we don't have to think too hard about plugging in some numbers. Now, we have to plug in the numbers the book gave us, but I would probably just choose 0, 1, and 2, personally. But they have asked us on 18, of course they asked us to use 0, but they've asked us to use -1, 0, and 1. Which are good choices. Okay, so let's start off by 0 first. That would, -3 times 0 is 0. 0 plus 2 is 2. So when x equals 0, y equals 2. Let's plug in -1. That will give us 3 plus 2, or 5. -3 times -1 is plus 3, and 3 and 2 are 5. And then let's plug in +1. So that's -3 plus 2, or -1. Okay, so we've got -1 and 5, and we've got 0, 2, and 1 and -1. So we'll just take a second and draw a fair representation of what that looks like. -1 for x and 5 for y. Say that's right there. 0, 2, and 1, -1. Yeah, they seem to fall in pretty good, even on this system that I drew there. Okay, maybe this one misses a little bit. But again, the idea when you're doing these on your graph paper, they will come out as nice as they should be there. Okay, well, the last few questions that we're going to look at here ask us to personally find our own 3 solutions or ordered pairs and then plug in and graph. So I've got a few of these picked out too. Here is question number 28. It's -3x plus y equals 1. And that's a +1 there. Now, what we need to do is get the, I don't think I did this one before. I think I did one close to it. Yeah. It's the same idea, but what we need to do is get 3x, add 3x to both sides. And then what we're really dealing with is y equals I added 3x to both sides. I got my equal sign looking like a negative there. So we end up with y equals, I'll just write it down below so there's no mistakes here, y equals 3x plus 1. That is what we're dealing with there. And the simplest points I can think of would be for x, maybe like 0, 1, and 2. Now, I could use a -1 and maybe have a little smaller graph, but these are just my normal simplest candidates when I don't have to worry about a fraction. Anyway, the y equals, when x equals 0, y would equal 1, and when x equals 1, we'd get 4. And when y equals 2, we'd get 3 times 2 plus 1, or 7. So now we're supposed to graph it. Should stretch my graph up to here for 7. Okay, so 0, 1. That's actually my y-intercept, by the way, and 1, 4, and then the last one is 2, 7. So there is a picture of y equals 3x plus 1. It's exactly what they want us to do, and this is actually the first method to draw these graphs. Okay, very carefully, we're almost at the end here. Take a look at 32 and 34. This is a really important, and I'll tell you, it's easy to sometimes mix these up, especially if you're in the class, in this algebra, in a beginning algebra class for the first time. But 32 asked us to graph y equals 3. And 34 asked us to graph x equals 3. So we need to remember, I'm sorry, x equals -3. So we need to remember that a graph of y is always flat or parallel to the x-axis. And maybe an even simpler way to remember that for the graphing is here's where x equals 3, right? Or sorry, here's where y equals 3 right here. And graphs of y are flat. So there's only one way that that graph can go. And it'll, of course, go through the point 0, 3. And anywhere on this line that I touch, y is going to have a value of 3. So just as a review, all y's are parallel to the x-axis. Okay, and I'm now going to label this as like y equals 3. Okay, how about 34, x equals minus 3? Well, here is where x equals some positive numbers, and on the left side of the origin is where x equals the negative numbers. And I'll give you the reminder that any graph of any graph of x is vertical or parallel to the y-axis. So here is the point where actually x equals minus 3, or it's the point minus 3, 0. And what I need to do then is just draw, I don't know why I got a squiggle there, just draw a line, straight line through the graph through that point of minus 3 and 0. And then I'll go ahead and label it as x equals minus 3. Okay, I've got 2 more to go, and here is question 36. Now actually I should do question 40. We've done one like 36, but I'll give you some points that might be helpful for you when you're doing 36. I would recommend for 36 that you use 0 and maybe 3 and minus 3 for x. Okay? Now, for question number 40, sometimes we just can't avoid dealing with fractions. And I think this might be one of the cases that happens. We can still draw the graph, but I'm limited in my choices. Of course, I'm going to use for x, this is 40 by the way, 36 I just gave you some hints on what to plug in. But I'm going to plug in 4 and minus 4 for x in 40. However, I've got the feeling that these are good numbers to plug in, but I've got a feeling that I'm going to end up with fractions, even though I try to avoid that. So we can still draw the graph, but it will not be so precise. It won't be as precise, of course, if we were locating ordered pairs of numbers that were not fractions. So when x is equal to 0, we would be looking for y equals 3/2, or 1.5. That's halfway between 1 and 2 on the y-axis. How about when we let x equal 4? Y equals minus 3/4 times 4 plus 3/2. Well, the 4 over 4 cancels out, and we get minus 3 plus 1.5, basically, which is minus 1.5, or minus 3/2. Minus 3 and 1.5 is minus 1.5, so minus 3/2. Now let's let x equal minus 4. Minus 4 over 4 is minus 1. Minus 3 times minus 1 is plus 3. 3 and 1.5 is 4/2. 3 and 1.5 is 4.5, which is the same as 9/2. 4 and 1/2 equals 4 times 2 plus 1, or 9/2. So those are the ordered pairs I'm going to have to find for this question here. And I'll do this on the top of the next page. And for 4, I've got a short memory here. We'll go back. 4 was minus 3 halves. And minus 4 was 9 halves. I'm pretty sure. Okay. And of course, remember, I can only approximate. You can do a better job with graph paper, but still, for example, 0 3 halves is 0 1 1/2. I'm pretty sure, I can't tell you exactly there, but that looks like it's about halfway between 1 and 2. Okay, so I'll label it just to make sure. That's supposed to be 0 and 3 halves. Now, 4 and minus 3 halves, or minus 1 1/2, say is about right there. I, again, can't be exact because I've only marked off in terms of whole numbers there. Okay, and then minus 4 and 4 1/2. 1, 2, 3, 4. 4 1/2 is 9 halves. So halfway between. I say that this point right here, and it's really not that bad, this would be negative 4 and 9 halves. Remember, 9 halves is 4 1/2. So 1, 2, 3, 4. Okay. So then draw a line through with arrowheads, and that would be the graph of y is equal to minus 3/4 x plus 3 halves. Now, you'll be doing 37 and 39, which are basically the same idea. Okay, but this is good because we're seeing every possible example, and we've brought the theory in on this before in terms of why we like to, whenever possible, graph whole numbers or ordered pairs that are both integers, no fractions. Okay, here's the last one, and see, this is just a look-at problem here. We've got 3 choices. If the graph is horizontal, we write h, and remember, any graph that's horizontal is going to be the graph of y equals a constant, which we called y equals b. And any graph that is vertical, we know that's x equals a constant, but we used a for that. And any graph that goes through the origin or vertical, they asked us to do v for vertical, okay, and o for origin. Okay, so here is 30, there are 4 of them here, and we'll quickly graph each one of them. So for 40, here's our graph. X equals 3, and then we have y equals 3. Then we have y equals 3x, and then finally we have y equals 0. Okay, well, here's x equals 3. That's the point 3, 0. It's where x equals 3. And of course, that's a vertical, graph of x equals 3 is a vertical line. So x equals 3, we write v. In fact, anytime it's just a graph of x, it's a vertical line. Now, the second one there is y equals 3. Let's say 3 is right here. This would be the point 0, 3, and it would run horizontal or parallel to the x-axis. So we will write for y equals 3 horizontal. Now, do you recall that when we have something like y equals 3x, Remember, we normally plug in 0 first. So if we had y equals 3x, and we plugged in x for 0, then the y would equal 3 times 0, which is 0. Okay, so that's enough for us to stop and say the graph of y equals 3x is going to go through the origin. So we'd write O there. Now the last one, and this is the last thing I have to say for the section here. The last one is y equals 0. Now, here is where y equals 1, and here is where y equals minus 1, and of course right here is where y equals 0. Just so happens that x equals 0 there also. Remember, all graphs of y are parallel to the x-axis. Okay, in this case, the graph of y equals 0 will actually sit right on the x-axis. It's going to look like this. In other words, it superimposes perfectly over the x-axis. And if you think about it, the graph of x equals 0 would superimpose over the y-axis. But we're only talking about the x right now, or the y right now. So the last one, the graph of y equals 0, it certainly is horizontal, and it certainly passes through the origin. So we write, oh, I'm sorry. You know what I just did? I looked at part of your 41 on that question, and I'm supposed to be doing, I've actually been doing your homework question. Not too good to get to the last question and make a little mistake. Of course, if I was in a class, somebody would point that out to me, but let's quickly look at 42. We had, it only will take a second. We had x equals a half, and we had y equals a half. It's the same idea. And then y equals a half x. And then finally, x equals 0. Okay, x equals a half would be a vertical line and parallel to the y-axis. Y equals a half will be a horizontal line parallel to the x-axis. Y equals a half x, if we let x equal 0, then y would equal a half of 0 or 0. So it passes through the origin, so we would write 0, I'm sorry, we would write O for that one. And the last one for x equals 0, x and y both equal 0 right there, but here's where x equals 1 and here's where x equals minus 1. So the all graphs of x are vertical, recall. So the graph of x equals 0 would be fit right perfectly over the y-axis running up and down there. So it would be vertical and run through the origin. Okay, well actually I did your 41 for you, but those are real important. In fact, that's one of the most important things in terms of the next section, because it turns out that lines that are vertical or horizontal have special cases for their slope, which we'll be seeing soon also. So 41 should be straightforward for you. We actually did most of those together on 41 and 42, and you have 43 to do also. Okay, well I'll be back shortly with the next section. Thank you.